let's start with a question, right? Let me ask you a simple question. Okay, so you guys can see my screen? Yes? No?
Yes.
Good. Okay.
Yep.
So I'm giving you a chalk, like a blackboard chalk, all right? This one. So in a physical class, in-person class, I gave a student the chalk, but now I have to do it and you trust me. So this chalk, if I twist it like that, if I twisting it like that until it breaks, I want you guys to guess how it's gonna break, all right? So I'm twisting this one then, twist and twist like that. How it's gonna break? Try to guess. It's gonna break like that. In the middle, it's gonna break like this one. Like let's call them A, B, C, and D. Or it's gonna break like the last one. Try to guess.
This isn't a super educated guess, but I would guess D.
D, okay. Oliver is suggesting it's gonna break like D. Like it's gonna be Sharpie in the middle, like that one. What else, guys?
I would guess B.
So Kirsten is suggesting B, okay.
I'd say C.
Okay, we have C. Any buyers for A? I'm selling it cheap. No one? $1.50? No A?
I want to change to A.
We changed to 8. Okay, Oliver changed to 8. Okay, you got it. So let's try. You guys agree? And so I'm gonna twist it and see how it's gonna break. Okay. One, oh, it's a hard one. Okay, let's see. This is how it breaks. How it looks like, guys. Can see, guys, or no?
Yeah, it's C.
It's C, all right? So if we measure this angle that it breaks, it's gonna be, so okay, let me, hope you guys see it, right? And by the way, when during an interview, when I gave this chalk to some faculties, to twist it, I was wishing that it breaks the way that I want it, because otherwise I couldn't get across my message, right? If it's not break the way that I want it, then I was in trouble. So it's gonna be break like that one. Let's put it aside. And if we measure that angle on things that break, it's gonna be exactly 45. So I guess Kirsten was sort of close. She said B, I guess. Sort of close. So B is the same, 45, but this is B. Now the same chalk. What about if I bend it now? So this time I'm gonna bend it, okay? I'm gonna bend it like that. So it is bending, that one was twisting. How is it gonna break when we bend it? Now try to guess.
I'd guess A.
Kirsten's suggesting A, okay. Others?
If it was a softer material, I'd guess D, because if it's like crushing itself.
Mm-hmm.
But I don't know how hard the chalk is.
The chalk is hard, right? Probably chalk on a blackboard is a hard material. So Emily, you're saying A?
Yeah, so I'd say A.
A, okay. What else? No other guess? Be brave. Just wild guess.
I think it's A2.
A2, all right. So let's try. Let's see if this time you were right. So I'm going to bend it down like that, right? So if I'm bending it down like that, yeah, you are right. Exactly 90 degree. Breaks like that, right? Okay, the same material, chalk, once I twist it and once I bend it, right? But I ended up with a different, basically, breaking pattern. So this one was like that, 45 degree. Okay, if I draw the stress element for each of them, the stress element for this one, because it was under bending, it is something like that. And the stress element for this one is under twisting is something like that. And if I do the same test, but instead of a chalk, I use another material like copper or aluminum or a steel, then I'm going to get a totally different pattern. So when I'm bending it, Emily was right, it's probably going to be something like D. When I'm twisting it, it's going to be exactly A. So if instead of a chalk, if I have, let's say, aluminum, the same thing's made out of aluminum, and I twist it, instead of breaking like, doesn't want to stay there. If I twist this aluminum, this one out of aluminum, instead of breaking like C, it's going to break like A. All right. So we see something is going on, and this is what we're going to figure out in this topic. We want to find out if you have a stress element, in which direction the stress gets maximum, right? Because things are going to break when we are getting to the maximum stress. And we want to know if at which direction the stress is getting maximum, right? So we draw the stress element for an element which is like a straight element here. But nobody asks us, why do you draw the element like that? Why don't you draw the element something oblique in an angle and try to find the stresses now for this element? Maybe things are going to be different, which you saw in this example, like for this chalk that breaks. So probably something was going on for an element which was in 45 degree. Maybe the stresses here was way too much bigger than the stresses over here and cause these things to break, right? And that's the objective of this topic for today. Now let's remove these chalk and things and switch back to our nice and clean screen. I guess Sajida prefer this one, right? Okay. So this is our goal. Why do we need to transfer stress? By transfer, I mean finding a stress for an element that it's not straight, it's rotating. Two reasons. First, as you saw in the example of chalk, we want to find out the maximum stresses. We want to see in which direction the stresses become element that things fail and breaks, right? And the second reason is always you are not lucky that our element like this cylinder that I'm showing you or this shaft that I'm showing here in this picture, that they are straight. Maybe this shaft is made out of two parts that they are glued together like on this line. And somebody asked us to find the stress on this line. Like over here, somebody asked us that, hey, I'm interested in finding the stress on this element. Okay. But we say, well, what we learned so far is just calculating the stresses for an element which is straight, right? Nobody told us how to calculate stress for an element which rotates. Or in example of, let's say, a cylinder, most of cylinder, sometimes we don't have a nice big plate and we weld together the plates, let's say, like an angle like that. Or maybe a vessel has been broken or tear, and then we weld them together along this line. So we know how to calculate sigma h. It has a nice formula, PR divided by T. We know how to calculate sigma A. We just learned PR divided by 2T. But we are not interested in them. We are interested in this sigma N and sigma T, like in this direction, N and T, which is like this angle is 30 degrees. All right? But we don't have any formula for this sigma N and T. Another application is, let's say, for wood. For wood, usually failures happen along the grain. And if somebody asks me to find the stress for these things, so from what we learned so far, we know, let's say at a point like that one, a point like that, or let me show it like that one. Let's say at this point, I'm interested in finding a stress. So we know that point, if we magnified it, it's going to be an element like this. And this element, we know how to calculate the stresses, right? We know it is under tension, compressions. And this compression, easily the stress is P over A, and A is this area, right? So we know how to do that. But they are asking us that, no, we are not interested in that. We are interested in finding stresses on this line, basically. Like on this line, basically. Or in other words, we are interested in finding a stress for an element which is something like that. So we want to know stresses here, because we realize that maybe these things, because it's wood, it's going to break under like along this grains, sorry. And also we may realize that there might be some shearing stress which we don't know. So that's why we need to basically something that we call it transferring the stress or converting the stress. By transferring, I mean you have the stresses in X and Y direction, like for example in this hoop example, or like in this wood grain example, you have the stresses in X and Y direction. Simply, you know your stress in X is 0 and your stress in Y is simply minus P over A. But you are interested in knowing the stresses in two new directions. Let's call them X prime and Y prime, all right? So that's why it is important. It is an important topic. So here is our objective. 3 main objectives. First one, we want to find out the stress when we rotate an element. That's the first objective, okay? So let's say we are in X and Y. This is the element that we have. And in a general case, we have sigma X, we have sigma Y, and we have tau XY on this image. Now we rotate element by angle of theta, you see here, and we want to find out the stresses, which we call them sigma X prime, sigma Y prime, and tau X prime Y prime. Okay, that's our first goal. Second goal is we want to know at which orientation these stresses becomes maximum. Is it in a vertical orientation the stress is maximum, or no? Like the example of chalk that you saw, when we rotate it 45 degrees, the stresses becomes maximum. So our next goal, which is more important, is finding the maximum and their angle, like how much we should rotate them, right? Either the shearing or the normal stress and their angle, right? We want to find out here like sigma max, and here we want to find out shearing stress max, tau max. This is our objective. Is it clear so far, guys, what we want to achieve here? Because the rest of the discussion is just a bunch of math formula. If you grasp what we want to do, then you're good. I assume you're good. I take the silence as being good. Okay. What are the formulas? So I warn you, there are a bunch of ugly formulas, but you can see they are super, super simple. So I have the element here, a 2D element here, and then I'm rotating it by theta, okay? So my stresses becomes, let's say this guy, sigma. Okay, first let's pick an axis. Okay. I need my axis somewhere here. Okay, it's here. Let's call this one, okay, already this image, call it X. Let's, this one that we already know, X. And let's call the other one Y. So this is X. And this is Y. Now we are rotating this element. And let's say the new axis, we call them X prime and Y prime. By the way, you guys can hear a lot of background noise or no? Or
No, it's good.
good? Okay, yeah, because I can hear a lot of background noise, but I have a good microphone. Yeah, these, I remember when I moved to UBC, I was joking to somebody, or somebody was just, I was talking to somebody, and he said, instead of University of British Columbia, he said, oh, welcome to University of Building Construction. And at that time, I didn't get the point. Then later I found what does he exactly mean, right? Here around, on campus, around the Save-On-Food, Westbrook area, probably you know where it is, close to that Save-On-Food. Many faculties live around this area. It's a nice area, but there are lots of construction. Like every year you see a new building like mushroom going up. Anyway, so that's why I was worried about the background noise. But if you're good, that's good. All right. So let's get back to this one. We have the element sigma x, sigma y, tau xy, and they are given to us. No problem. Don't forget about the sign. Always we show like this tension, but if they are under compression, don't forget that negative sign, right? And also tau xy, I told you the sign, right? Positive or negative if they are rotating element, clockwise or counterclockwise. But I'll review it again if you forget from previous lectures. So this is sigma x prime, this is sigma y prime, and this is tau x prime y prime. And we don't know their values, and we don't know their direction. Maybe after we rotate an element, they become compressive, or they become zero, we don't know, right? So here are the formula, or the main formula which we need to know. Sigma, I'm just gonna write them down here. Sigma x prime is gonna be sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. Sine 2 theta. And then sigma y prime is very similar to that one. Sigma x, sigma y divided by 2, except here is minus. Sigma y, 2 cosine 2 theta minus tau xy sine 2 theta. And tau x prime y prime is going to be equal to sigma x minus sigma y divided by 2 sine 2 theta, the cosine becomes sine, and tau xy cosine 2 theta. Ooh, ugly formula, right? When I'm teaching in a physical setup in a classroom, I usually impress my students by just writing them out of memory, not my notes. But here probably you say, okay, this guy has some notes next to him, right? But usually my style is no note. So this formula looks ugly, but there is a pattern to them, right? And you don't need to memorize them, by the way, because your exam is going to be open book. So that's it. You have the element in X and Y, you rotate it by theta, you plugged in this formula, plug and chalk. That's simple, right? You get sigma x prime, y prime, and tau x prime, y prime. Let's move back to the example at the very, very beginning. Let's say somebody gave you a cylinder and asked you to find the stresses on the welding line. Like let's say they weld this cylinder on this line, which is 30 degree. So the theta is 30 degree. You have your sigma x and you have your sigma y. And in this example, tau xy is 0, right? Now you can find sigma n and sigma t. It's called sigma n and sigma t. That's up to you. You can call them sigma x prime, tau x prime, y prime. Okay? I'll solve one example, don't worry. So this is just the naming. Some people call it NTs. Your textbook call it x prime, y prime, which is more common. Okay, and we go with that one. Okay. Any question so far, guys? It looks simple, right? Nothing complicated about it. Just don't forget that it is 2 theta. I've seen many times a student, when we give them like angle 30 degree, they just plugged in cosine 30. No, it is 2 theta. So far good, everybody. Go ahead.
So just like clarifying, so basically we're finding the stress like when it rotates, and the maximum stresses would be where the angle, like
okay,
the angle where it would have the largest stress.
Yeah. So Sajido is asking, we're finding a stress when we rotate an element, like the example of cylinder. Somebody asked us to rotate it 30 degree, but like in the example of chalk, how we can find the angle when these things become maximum? Well, if you have functions like this, how can you find the maximum? You just take the derivative, right? You take the derivative and you can find the theta that these things become maximum, all right? Which is our next topic, okay?
That makes sense. Okay,
all
thank
right.
you.
Yeah, but simply in a simple concept, when you have a function like this, like they are a function of theta, right, guys? You see this sigma x prime, sigma y prime, and tau x prime, y prime, they are a function of theta. It means if you rotate your element 10 degree, you get some numbers, 20 degree, and some numbers, 30, and so on. You can go from 0 to 1 complete rotation, right? Now the question is, when these things become maximum, we take the derivative and we can find the maximum, which we are going to discuss it more now, all right? It seems simple now, and the story was supposed to end here, basically, until this guy, I guess I have an image of him somewhere. Yeah, this guy, his name is Mohr. He said, wait a minute. It was like 100 years ago. He said, you guys are lucky because you have a calculator, right? Like this one, right? And simply, if I give you a problem and ask you to find it at angle theta 25 degree, you say no problem. 30 degree, no problem. 60 degree, 55 degree, you just plugged in, and 10 seconds later, you give me the answer. But this guy, after he adjusted his mustache, he realized that, well, for any angle that he wants to calculate these stresses, then he has to go to a big book, find the sine theta, for example, for theta equal to 25 degree. Imagine 100 years ago, there was no calculator, right? And finding this sine and cosine was like a headache. There was like, if you look at the old books, at the end of the books, there are like 100 pages of this sine, for example, sine 1 degree, sine 2 degrees, sine 3 degree, cosine of 4 degree, and so on. And then the trouble was the start if somebody asked you to find the cosine of 25.5 degree. Then you have to do lots of calculation to find that, right? It was a headache. So he, in fact, doesn't like this formula and he said, I need to do something about it. Okay, so this is what he did, and the headache starts from now, and that's why most of Mech 260 students, they don't like this guy. But believe me, you're gonna like him the way that I explained. So this guy wanted to get rid of this sine and cosine, and he was smart, and this is what he did. Okay, what he did, he went to the next page, of course. He just rearranged this formula a little bit. So what he did, the first formula, sigma x prime minus sigma x plus sigma y divided by 2 is equal to sigma x minus sigma y cosine 2 theta tau xy. So the first equation, he just moved this part, right, the sigma x plus y to the left side, okay? And then he just doesn't look at the second one, and then the third one, he just keep it as it is. Okay, let me write it down as it is. Tau x prime y prime equal to sigma x minus sigma y divided by, oh, we have a sine 2 theta here. Sine 2 theta minus tau xy cosine 2 theta. Okay, nothing so far special about it. Then he take each side to power 2, like this one, right there. And then he adds them. Sigma x prime minus sigma x sigma y divided by 2 plus tau x prime y prime 2. Okay, he add them up. I'm just going to spare some math here for you, and he got this one. You can try it later. It's just because we have sine and cosine power 2, and also we know that sine 2 theta from trigonometry, if you forgot, is equal to 1. We're going to get to sigma x minus sigma y divided by 2 power 2 plus tau xy power 2. And now he was happy. Why? Because see, there is no, not that one, there is no cosine and sine, right? He doesn't like sine and cosine. Okay, so this is what he got. But how he's gonna use this basically relation, right? So what he found is that there is a relation between this sigma x prime, tau x prime y prime, and this sigma x y and tau x y. And there is no sine and cosine, right? He got rid of this sine and cosine. So he opened his math book, maybe Math 101, and then I'm gonna remind you of something if you forget. So recall okay, let's say if I have, forget these stresses for a moment, and let's say you have x, y here, and let's say we have a circle over here, and let's say this circle, the center, let's say its distance on x and y, let's say they are a and b. And let's say the radius is r. R, and let's say this distance is a and this distance is b. Okay. If you forget, a circle has an equation. A circle that happens to be its center at point O, which is like its coordinate on x and y is a and b, and the radius is r, has an equation which has this form. I'm writing down here, x minus a power 2 y minus b power 2 is equal to r squared. This is an equation for a circle. I guess you guys studied this somewhere in your math 101 or 102 or somewhere, right? Or in geometry somewhere, hopefully. You did or no?
Yeah, we did
You did.
in
Okay.
101.
Okay, good. So this is what this guy Mohr did, right? Otto Mohr. He looked at his math 101 notes. And then he also noticed if this circle happened to be on the x-axis, like this one, right? Now it means that the basically b is 0, so x minus a plus y squared is equal to r squared. And he said, wow, this is how it's going to be there. His equation, like the one at the top, right? It looks like this guy. Do you guys agree? Except this a is this one, and this r is this guy, right? And instead of x and y, we have just the name, sigma and tau. So this is x and y, and we have sigma and tau. So this is what he basically concluded, that these things can be on a circle. Let's draw them on a circle. So draw a circle. Our coordinate, this time we call them sigma and tau, or tau x prime y prime and sigma x prime, right? Remember this formula that we have? And by the way, if we do the same things that we did here, instead of sigma x prime, if we use the second equation, we get the same thing. So it's going to be sigma x prime or sigma y prime. So we are going to end up with a circle that is basically is on the x-axis. And by x-axis here, don't forget, it's sigma x prime. We don't have any x and y here. Remember, geometry x and y is just the rotation of this element. We're talking about sigma x prime, sigma y prime, and tau x prime, y prime, right? Two different things. And this thing has a radius r, and also the center happens to be here. So this is the center, sigma x plus sigma y divided by 2, and this is a radius. So let's, for simplicity, call this one, because I don't like to write every time this one. Let's call it sigma average. It looks like average, right? Sigma x plus sigma y divided by 2. And then we have the radius. So we have a formula for them then. Let's summarize them here. Sigma average is sigma x, sigma y divided by 2. And r here is the square root of sigma x minus sigma y divided by 2 tau xy divided by 2. All right, that's Mohr circle. So far, is there any question? I hope you guys follow what we did, basically. This is not what we did, this is what this guy did. Okay, this guy, right? So he got rid of these basically theta by just simply figuring out that the stresses they are on a circle. Now, if somebody asks him that he wants stress on 30 degree, he doesn't need to worry about a calculator. He just finds the 30-degree angle, and he just read the numbers from here. Okay, which I will show you in the next step. But is there any questions so far? because if he realized that if everything is on a circle, this tau x prime y prime, then he doesn't need to go to sigma x prime and y prime. Question? Are we good? All right. From Mohr circle, right? And we know where it comes from. Now, let's say how we can use it. So there is like a nice approach which simplify things for us, and we can always use these 8 steps to draw the Mohr circle. All right, let's do them together. First step, decide for an x and y references. So you have your stress element like this one, right? Let me move these things down there. So you decide for an x and y. This is something that we did in previous topics in the stress combination topic, x and y. This is our element. Step number 2, find sigma x, sigma y, and tau xy. Previous lecture, right? X, y, sigma x, sigma y, and tau xy. This is so far good. And now, step number 3, draw a set of sigma tau coordinate, okay? So draw a set of, let me draw it over here. Sigma and tau, all right? So this is then, remember, this is sigma, this is tau. This is our coordinate for stress. This x and y, remember, this is the geometric coordinate. This is for the element, okay? So step number 4, plot point sigma x minus tau xy and call it point V, okay? So you have a bunch of numbers. Let's for now say that maybe this is point V, okay? Point V is sigma x and minus tau xy, okay? So just keep in mind, if tau is negative, negative multiplied by negative is going to be positive, so this point V is jumping up, right? But for now, because everything is positive, so V is down there. I just picked 2 random numbers here. So let's be organized. So this is the point V. So far easy, right? And then step number 5, find the point sigma y tau xy and call it point H. So if it is plus tau xy, it means it is mirror of this one. And let's say for now that this point is somewhere maybe around here. So, okay, this is point H, and this point H is sigma y and tau xy. Again, just 2 random numbers. Maybe this point H is, maybe sigma y is bigger, is around here. That's fine. Maybe it's a negative number. If it is compression, it's over there, like here. But that's fine, all right? It can be anywhere. Doesn't change things for us. So then this is our this step, all right? Just keep in mind that this sigma y is at the same high, like because it is plus tau xy, right? As the point H, point V. And then what is the next step? Step number 6, draw a line between V and H. We do that. We can do that, right? It's easy. And it says that this established the center C of the circle, basically this point. Okay, this is the center of this circle, point C. So draw the circle. If that's the center, if you have the radius, just simply draw the circle. Let's do that. So Looks like a watermelon. No, that's not bad. It's a circle, all right? So that's more circle. So now it says, so far, we've just followed these steps. 8 is the sort of the guideline that how we are going to use this circle. Step 8 says, well, good for you, you have the circle. So it says point V is basically the point that you have the current state of stress, okay? So point V, in fact, is the current state of stress. Why I cannot draw it? So it is our sigma x, sigma y, and tau xy. Draw it over here for you. Okay. And any other points, you just treat this, basically this, I cannot draw. Yeah, just treat this line and this point more like an arrow. Like this arrow, more like a gauge. And wherever you want to find the stress, let's say if somebody asks you to find the stress for an element which rotates 30 degrees, let's say a new element. Let's say this element. Which this angle is 30 degrees, and you want to find out the stresses, all you need to do, this handle, treat it more like a gauge and rotate it 60 degrees. That's the trick, not 30 degrees, 60 degrees. So it gets you to a new point. So this angle, 60 degrees, okay? Twice as what you are asked, 30, 60. So you get to the new point, this new point, you just read the numbers from this new point, that's all. So you read the value that you can see, okay, on the x-axis and on the y-axis. Whatever number you are reading here is going to give you the sigma x prime, sigma y prime, and tau x prime y prime. All right, so remember it is here, over here we can find what number. You call it sigma x prime, okay? The bottom of this arrow over here gives you sigma y prime. And so this is sigma y prime, all right, this point. And tau x prime y prime from here. So this method is all geometry. We need to draw things perfectly, and then we just read the numbers from these graphs, basically, okay? No calculator involves this one. So I review it one more time. Up to step 7, I believe is super easy. You just draw your circle, that's all. Then you treat this, basically this line as an, more like a gauge, right? This line, you treat it more like a gauge, which you can rotate it to whatever position that you want. If somebody asks you stress for an element which is 30 degrees, you rotate it 60 degrees twice. The new points, you just read the numbers, right? The number that you are reading from this tip of this arrow gives you sigma x prime and tau x prime y prime. And the tail of this arrow gives you sigma y prime, basically. All right? If somebody asks you the stress in 22 degree 0.5, 22.5, but rotating clockwise, you rotate your arrow twice, like 45 degrees in the same direction clockwise. So you get to the new point and you read the stresses, all right? So probably now you should have this question that, well, what the hell, if I have a calculator now, and if I have all these simple formula, right? Who cares about all these drawing circles and stuff? Well, unfortunately, we have to, because you have to pass this course, right? Later, you are okay. You just get rid of this Mohr circle and use this formula. But for now, you have to learn how to use the Mohr circle, which I'm going to solve one example now. So you see how the question is going to be asked. Okay. And find stresses. And by the way, in future also, this Mohr circle, it can be more impressive. Let's say if you provide a report and you calculate the maximum stresses and so on, then drawing all these circles is fancier, right? You feel like an engineer. You draw these circles and find the numbers. I like it. I don't know about you guys. But anyway, for exam, you need to learn it. So that's how we construct Mohr circle, all right? One more step before I solve examples. If you remember, Sajida asked a question. She asked, how can we find the maximum stresses? And I told her, we take the derivative, and she was happy, right? But taking the derivative from those equations is not really that simple. Take the derivatives, plug in those numbers, it's a headache. But let's see if that Mohr circle can help us. Let's take a look at this Mohr circle. So if any point on this circle gives us new information for sigma x prime, okay, let me write it down. If any point gives us sigma x prime and tau x prime y prime, right, then where on this circle the sigma becomes maximum? Can you guys tell me? So again, my question is, any points here on this circle represent a new element, an element that we are rotating, right? Where on this circle my stresses becomes maximum?
On the x-axis.
On the x-axis, good, yeah. So Sajida is right. If you look at these circles, like over here, do you guys agree that this is a sigma max? Let's take a look. See this arrow, we are here right now, right? At this point V. If we rotate, get to that point, sigma is become, if toward that point, sigma becomes bigger, bigger until we get to that maximum. Then it becomes smaller, smaller. And then if we keep rotating it, at this point, it becomes minimum. So sigma mean, right? What about tau? Where tau becomes maximum? Remember, y is the tau, right? So right now, tau is like here. This is minus tau xy. Where tau becomes maximum?
At the top of the circle?
At the top of circle, exactly. So see, this is where we are as we are rotating. At the top of this circle, or the top here, we have tau maximum. So let's see, let's see if we don't look at the formula, we can figure out this max and mean. Let's see, just geometry, just from geometry. Let's see what we have. So I know the distance, let's say, from point, let's call this point A, and let's call this point B, right? And over here, let's call it O. I know the distance from O to B. O to B is sigma x. Okay. Sigma x. I know the distance from O to A, it is sigma y, right? This is how we draw it. Point A was tail of these things, which was sigma y, okay? At any point, if you cannot follow, guys, or if I'm making a mistake, please tell me. So I have the distance between O to A. I have the distance between O to B. I know C is in the middle of A and B. So OC has to be sigma x plus sigma y divided by 2. All right? What else do I know? I know also the distance between C and this sigma max. Let's call this point D. The distance between CD is in fact the radius. Remember, this circle has a radius of Mohr, right? Mohr circle R. So, do you guys agree that I can write down sigma max to be equal to sigma average plus R? You guys agree? See, this is sigma max, right? The distance between O to D is equal to OC plus CD. It is equal to this guy, which we call it sigma average, plus R, the radius. Radius of this circle is R, right? CD. What about sigma mean? Sigma mean is sigma average minus R. See, we found the maximum and minimum stresses without any trouble, without taking any derivative. So after all, maybe this guy, Mohr and Mohr circle is not that bad. What about tau max? How much is tau max? Can you guys tell how much is tau max? Just look at the geometry.
Is it just R?
Yeah, exactly, Thomas. So it is just R. So we found tau max, we found sigma max and mean without taking any derivative, all right? One last thing, we need to know the angle, okay? So right now we are at point V. The maximum happens when we are rotating how much? This amount on this angle, on this circle. Let's call this one 2 theta. So if you notice, anything on the Mohr circle is 2 theta because the base of Mohr circle was these equations, right? These equations, let's move back, and they have 2 theta. So everything on Mohr circle is 2 theta. So this angle is 2 theta. And can we find this angle? Why we are interested in finding this angle? Because we know we are at point V. We want to know how much we need to rotate to get to this maximum point. So we need to find this 2 theta. Can we find it? Let's look at this triangle, CBV. So in triangle CBV, what do I have? Can I write down tangent of 2 theta is equal to what? Is equal to VB divided by BC, right? VB divided by BC. VB is tau xy. What about BC, right? What about BC? So I know OB, I know OA. So AB, I'm just gonna write it down over here at the top. So AB is gonna be OB minus OA, right? Look at just the geometry. OB minus OA give me AB, right? So that's AB, and CB is half of that because C is in the middle, okay? But we know OB and we know OA, so this is sigma X minus sigma Y. So it means here I'm gonna just have, let me write it down, smaller font. So at the bottom here is gonna be tau xy sigma x minus sigma y divided by 2. All right? So in fact, we found the angle where the maximum stress happens. And that's all. You're done. Happy? See? No derivatives, just geometry. And I know it's because it's a lot of material now, it may look complicated, but it's not really. It's straightforward, in fact, super, super easy. And bunch of formula and then the Mohr circle. Okay? So let's see if you guys have questions. You're good? Okay, I assume you're good. So do you guys notice anything special about sigma max and sigma mean? Where the maximum and minimum happens? I wanted to hear. There is no shear. So where the maximum and minimum happens, there is no shear stress, right? See, they are on the x-axis, on the horizontal axis, and there is no shear. So people decided for a fancy name for this maximum and minimum, and they call them principal stresses. So what is principal stress? Where there is no shear. At an angle where there is no shearing stress. That is called principal stress, which is nothing except that the sigma max and sigma mean. And people call them sigma principal 1, sigma principal 2, right? So like on this axis, they call this one principal 1 and principal 2. And this angle, people call it theta principal. And people call them principal because these are where the maximum happens. These are where the breaking things happen, right? And that's why people call them principal, because they have to be the main focus of when we design something, not the sigma x and sigma y, these principal stresses. How we calculate principal stresses? Easy, right? Sigma P1 and P2, they are like exactly sigma max and sigma mean, which we just found them. Sigma average plus minus R. That's all. How we can find this angle of principal? We just found it. Tau max divided by sigma x minus sigma y divided by 2, which I just bring these 2 up there. Good? Guys are happy with that so far? I hope. Okay. So the lecture is done. Now an example. So let's see, you guys still have energy or no? It's quiet. No energy left? Headache? Let's see who left in the class. You guys are all here, but you're quiet.
It's a lot of numbers.
It's a lot of numbers. I can see. But do you guys have energy to solve this one?
Yeah.
Let's do it. Yeah, let's do it.
Sounds good.
Okay? Yeah, okay, let's do it. It's not difficult, really. It's easy. We can do it. Let's do it quickly. Let's see with the people who are quiet in the class. Jessica, you're good?
Yep.
You're good? Okay. So, Vince, you're good?
Pretty good.
Good. All right. So, sorry, guys, that it took longer, but I had to explain that much because now I'm sure after you review this topic, you're going to master like the most difficult and challenging topic in mechanics of material, and you're going to show off to your friends because many students have problem understanding this one, but you realize, right, it's nothing, right? And let's see it in this example quickly, and hopefully we'll be done soon. So this example is going to be something that you're going to see exactly similar to it in your final exam, but different numbers. All right, let's see if we can do it quickly. It has 3 parts. In part 1, we are asked to find the stresses when we are rotating this element 30 degrees. All right, just using the formula. Okay, so always there is a main step, the first step, which if we take the first step wrong, then we are in trouble, right? Always in life also there is a first step. I'm just joking. So, but or maybe there is. So the first step is writing down the sigma x, sigma y, and tau xy correctly. Sigma x is 60 and it is positive. Sigma y is minus 20 because it's compressive, right? It's negative. What about this tau xy? Is this the one that confused many people? I'm going to write down minus 30, and now you're going to say y minus. So if you forget, it was in lecture on Tuesday. We said we need to have an agreement together, and that agreement was you look at a stress element, you look on the side, on the vertical side, if the stress try to rotate the element counterclockwise, consider them positive. So this is positive, counterclockwise. If, for you to remember, okay? But if the stress element try to rotate it clockwise, then they're going to be negative. So this is negative because the stress is more like these stresses, we treat them more like let's say a couple, right? It's rotating it, spinning this one clockwise, so we consider it negative, this one is positive, okay? So that's where this negative comes from. And yeah, if you make a mistake here, this negative sign, all of your calculation is gonna be wrong, which for exam, you lose credit. In practice, in future, believe me, this negative sign can kill people. A while ago in the company that I used to work, I was sort of assigned to analyze a report which come from a university from US, which they built a sort of a bridge, a small bridge inside a campus, but the bridge collapsed and killed 2 people. And believe it or not, it was a simple mistake calculation error in finding the principal stresses. Yeah. So probably if I can share that later with you, I would check if it is not confidential. Probably not, because 2 years passed. So if we are done with that, then the rest is just plugging the numbers. Sigma x prime, so theta is 30 degrees. Sigma x prime is going to be sigma x, and the formula that we have, sigma x plus sigma y. Don't forget it is negative divided by 2 plus sigma s minus. I put these minus things here so you know this is cosine 60. And then we have tau xy, which is minus 30 sine 60. If we do our calculation, we're going to get 14. Sigma y prime, things the same, except this one is negative there. We get 66. And tau x prime y prime, it's going to be 60 minus 22 sine 60. And then this one is minus. We have another minus. Cosine 60, give me 50 megapascal. Okay, so the question usually asks us to draw the stress for the new element. So the new element is gonna looks like this one then. Okay, so what are the stresses? Sigma x prime is positive. Sigma y prime also is positive. And what about tau x prime y prime? It is positive, and since it is positive, it has to rotate the element how? Counterclockwise. So this is 14. This guy is going to be 66 megapascal. And this guy is going to be 50. If we find the element on the side, then the rest is just, I told you before, right? The tip of these arrows come together, and this is like that. So this is our new stress element. Okay, we just use our calculator, and we got to this one. Question so far for this? Are we good? Okay. So part 2, usually it asks to find principal stress. That part is very easy. Sigma, you find the sigma average, which is 60 plus minus 20 divided by 2 gives me how much? 30. And then find the radius. Radius has a formula, sigma x minus sigma y divided by 2 plus tau xy squared. You plugged in all the numbers, and it gives you 50. The unit is megapascal, okay? So if you have the average and R, then sigma principal 1 and 2, they are sigma average plus minus R. So it means your sigma principal 1 is how much? It's sigma average. So this is principal 1. It's going to be 80, right? And sigma principal 2 is going to be minus 20. So it's negative, but that's fine. Okay. You guys okay with this part? See, very simple, right? This is our principal stress. What is the angle this principal happens? You can find it. Tangent to theta principal is equal to tau xy divided by sigma x minus sigma y, and we have a 2 here, don't forget that 2. And it gives you theta principal 37 degree. Meaning, if you rotate this element 37 degree, you get to this principal stress, and that's where it is important the breaking happens, the failure happens.
Quick question.
Go ahead, please.
Maybe I'm doing a math wrong in my head, but is sigma average not 20 megapascals?
Oh yeah, you're right. Thank you, Thomas. So it is 20. Then you're right. So it's gonna be 20 plus 50, 70. Thanks for checking. So this is 20 minus 30. All right. I guess I'm also getting tired, but we are done almost. So far seems good, right? Part 2. But let's move to part 3. Part 3 is more circle. Very simple. I just want you guys in your exam to draw a circle for me. It's not difficult, right? But I want a clean circle. So buy one compass, all right? Don't do it by hand. If you don't have a compass, buy one. All right, it's cheap. It's $5. You can buy it from a Staple. Or you just use maybe a piece of thread and you just draw a nice circle. Okay, how do we draw more circle? 7 steps. Let's do it. So first, draw the axis. Sigma axis. And the tau axis. Okay, so this is sigma and this is tau. Okay, and then if you are using a grid paper like me, that's good. If not, you just use your ruler. decide for a scale. You don't want to draw, instead of a circle, a watermelon for me or ellipse for me, right? So decide for a scale so things looks nice, right? Let's say if you have like 60, 30, and 20 here, let's say in my grid paper here, every, let's say, section here, consider 10, right? So we need 2 points, point V, remember it was sigma x and minus tau xy. So then it's going to be 60 and plus 30. You have a negative and another negative. And then point H, which was sigma y and tau xy. Sigma y minus 20 and minus 30. Let's find these 2 points. So 60, right? I said each of these to consider 1, 2, 3, 4, 5, 6. So I am here and then 3. So this gives me point V. And this gives me point V. And point H minus 20 and 30. This gives me point H. All right, guys? So point V and point H. This part is easy. We can do it easily. Sorry. So, and again, if you are not using a grid paper in your exam or in future somewhere, you just use your ruler and just divide this one based on numbers that make sense. If, for example, this number instead of 60, 30 was like something like 500, 2000, then consider each section to be like 100 megapascal. Doesn't matter because we're just using a scale here. And then the next step was just to connect these 2 lines together, these 2 points together, V and H, and then draw a circle which its center is like that point, and passing through point V and H. This is the Mohr circle, and we're done. C. Okay? And this is our sigma max, or sigma principal 1. Let's see if the number we found is right? Point V was 60, and I can see from here I'm just 1 point, so it's going to give me 70, almost, right? Because it's graphic here now. Now I'm here. Maybe my circle is not perfect, but 20 plus 10 is give me 30. Let's draw the circle a little bit better. Anyway, so this is principal 2, which gives me 30. Let's see, this is the number we got. Yeah, 70 minus 30. This is from theory. This is from just geometry. Minus 30, it is over here, all right? And if you measure the radius here, probably, if you count these things, probably you should get whatever we got for R here, which was how much? R was 50. Yeah, let's count them. 1, 2, 3, 4. 1, 2, 3, 4, 5. Yeah, almost 70. So R 70. That's it, done. So this is Mohr circle. So example, 3 parts. Part 1, you just use simply the sigma x prime, sigma y prime, and tau x prime, y prime. Use the formula, done. Step 2, finding the principal stresses using simply the formula. We have a bunch of formula, sigma average, R, done. Step 3, drawing the Mohr circle. This is the Mohr circle. Just find 2 points, V, H. The rest, draw a circle between these 2 points, V and H. The Mohr circle in your exam is a good thing because you can check your number here, right? You just roughly read your number here, like 70 minus 30. And if you've done any mistake, for example, instead of minus, you get a positive number, then you say, oh, I made a mistake somewhere, and you come back and correct it. So that's gonna be sort of a checking things for you guys.